Take 1 and divide it by 998,001, a single, unremarkable fraction. The number underneath is 999 squared, if you want to check it. Now look at what its decimal actually does. It begins 0.000, 001, 002, 003, 004. Split those digits into groups of 3, and something jumps out. The groups are just counting. 0, then 1, then 2, then 3, then 4, then 5, marching straight up, 1 per block, as if the fraction were reciting the whole numbers to you in order, a plain division problem. And out the other side comes the counting sequence itself, laid end to end. Most fractions give you noise. 1/7 is a short repeating scribble. 1 over a random 6-digit number is a long stretch of digits with no visible order at all. This one is different. It is handing you the natural numbers, 3 digits at a time, and it does not stop after a few. It keeps counting, far past where any accident could reach. To be sure this is real and not a trick of the first few digits, keep reading. The blocks roll on exactly as promised. 9, then 10, then 11, 12, 13, on into the 20s and the 30s without a stumble. When the count reaches 100, the block simply reads 100. At 200, 200. Every single 3-digit number you can name shows up right where it belongs in the count, in perfect order, all the way up into the 900s. This is not the fraction getting lucky for a moment. It is doing this on purpose, block after block after block, hundreds of them in a row. It helps to see just how far this goes. There are 1,000 different 3-digit blocks, from 000 all the way to 999. And this single fraction marches through very nearly all of them, in order, inside one turn of its decimal. Try to picture writing that by hand. 3,000 digits, each trio one larger than the last, never slipping. No human copying numbers would stay perfect that long. Yet the division does it effortlessly, because it is not really copying anything, it is computing. So you are looking at a genuine phenomenon, not a coincidence. Somewhere inside this one modest fraction, the entire counting sequence is encoded, and reading the decimal just plays it back, which raises the obvious question of how a lone division could possibly know how to count. But before we answer that, there is one more thing to notice, and it is the detail that makes the whole thing worth a closer look. The counting is almost perfect. Almost. There is exactly one number missing. Follow the blocks all the way up toward the top of their run, and watch carefully right at the end. The count climbs through 995, 996, 997, just as you would expect. And then the very next block is 999. It skipped 1. 998 never appears at all. The sequence counts flawlessly from 0 straight up into the high 900s. And then, one step from the end, it drops a single number and moves on as if nothing happened. After 999, the whole pattern resets to 000 and counts up all over again, forever, repeating every 999 blocks. So the fraction is not quite reciting all the 3-digit numbers, it recites all of them but one. And that missing 998 is not a flaw or a rounding slip. It is a genuine, permanent feature of the number, and once you understand where the counting comes from, the missing block explains itself perfectly. So let us find out where a fraction learns to count. The secret is a single, famous identity, and it has nothing to do with decimals at first. Start with a plain infinite sum. 1 plus 2 times some quantity, plus 3 times that quantity squared, plus 4 times it cubed, and so on, each term stepping up its multiplier by 1. It is the counting numbers used as coefficients. That whole infinite sum collapses into something astonishingly compact. It equals 1 divided by the quantity of 1 minus your value squared. That is a standard result you can prove in a line or two, and the important part is what sits in it. The counting numbers on one side, a clean little squared fraction on the other. If you have never seen why that sum collapses, here is the whole argument in one breath. Take the plain geometric series, 1 plus the value plus its square plus its cube and on forever, which everyone learns sums to 1 over 1 minus the value. Now differentiate both sides, just once. The left side turns into 1 plus 2 times the value plus 3 times its square, exactly our counting coefficient sum. The right side turns into 1 over the quantity of 1 minus the value squared. Two sides of the same coin. The counting numbers appear the instant you take a derivative of the simplest series there is. This identity is a machine. On the left, it has the sequence 1, 2, 3, 4 written into the coefficients. On the right, it has a simple formula. So if you could somehow turn those coefficients into the digits of a decimal, the formula on the right would be a fraction that spells out the counting numbers. That is exactly the move. All we have to do is choose the value that turns coefficients into 3-digit blocks, and the whole mystery unwinds. To make each coefficient land in its own block of 3 digits, feed the machine 1,000th. Set the quantity to 1 over 1,000. Each higher power of 1,000th shifts you 3 more decimal places to the right, which is exactly 1 fresh block of 3 digits. So the coefficient 1 lands in the first block, 2 in the next block over, 3 in the one after that, each number tucked cleanly into its own 3-place slot, spelling the count. And the compact right-hand side, with 1,000th plugged in, works out after a little arithmetic to precisely 1 over 998,001. The squared fraction becomes our fraction. That is the entire secret. The decimal counts because it is secretly that infinite sum of the counting numbers, wearing a fraction as a disguise. And now the counting is not a wonder anymore. It is bookkeeping. Every whole number is a coefficient. Every coefficient sits 3 places apart from the next, and the decimal just reads them off in order. Which finally lets us explain the one number that goes missing. The missing block is not random. In fact, you can predict it, and it comes down to a collision between 2 blocks. Here is the trouble. The counting numbers do not politely stop at 999. The sum keeps going. The next coefficient is 1,000, then 1,001, and those no longer fit inside a 3-digit block. 1,000 needs 4 digits, so when its turn comes, that extra 1 spills 1 place to the left, landing right on top of the block just before it. That block was carrying 999, and the stray 1 bumps it, and the carry ripples back exactly far enough to nudge the earlier 998 up into a 999. The block that should have read 998 gets overwritten by the overflow behind it, so the gap is a carry, plain and simple, and it always sits 2 below the base of the blocks. For 3-digit blocks, the base is 1,000, and 2 below is 998. That prediction is worth keeping because it tells you exactly what to expect from the fraction's smaller relatives, which do the very same thing on a smaller stage. This fraction is not a one-off curiosity. It is the middle child of a whole family, and the little ones are easier to see through. Take 1 divided by 81. 81 is 9 squared, the 1-digit version of the same construction. Its decimal reads 0, 1, 2, 3, 4, 5, 6, 7, and then, right on cue, it skips straight to 9. It counts the single digits and drops the 8, because 8 is 2 below 10, exactly as our rule predicted. Step up 1 size to 1 over 9,801, which is 99 squared. Now the blocks are 2 digits wide, and it counts 0, 0, 0, 1, 0, 2 on up, and skips 98, which is 2 below 100. Same machine, same missing number rule, just a different block width each time. Line them up, and the pattern is unmistakable. 9 squared skips 8. 99 squared skips 98. 999 squared skips 998. Each one is a square of a string of 9s, and each one recites the counting numbers in its own block size, minus the single value 2 below the top. It is the same idea, printed at 3 different scales. Once you see the fraction as a machine that plays back a sequence, you can change the sequence. Counting is only the simplest thing to encode. There is a slightly different identity whose coefficients are not 1, 2, 3, but the Fibonacci numbers, where each term is the sum of the 2 before it. Feed that one the same 1,000th, and out comes a fraction whose decimal recites Fibonacci in 3-digit blocks. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. The fraction is 1 divided by 998,999, almost a twin of our counting 1, and its decimal quietly lists the most famous sequence in mathematics. And this cousin breaks for the same reason ours does. Fibonacci grows fast, so it does not take long before a term needs more than 3 digits. The clean recital runs 0, 1, 1, 2, 3, 5, 8, and onward, staying perfect right up to 610 and 987. But the very next Fibonacci number is 1597, and that no longer fits in 3 digits. Once the numbers climb past 999, the blocks overflow, the carries start piling in, and the clean recital dissolves into ordinary-looking digits. Both fractions tell a perfect story right up until the sequence outgrows the space it was given, and then the carries take over, which is the honest way to describe what these numbers really are. It is tempting to call this magic, so it is worth saying plainly what is actually going on. 1 divided by 998,001 is a perfectly ordinary rational number. Its decimal has to repeat, like every fractions does, and this one repeats with a period of 2,997 digits, which is exactly 999 blocks of 3 before it starts over. Inside one full period, it recites the count, skips its one number, and loops. There is nothing infinite or mystical stored in there. The counting only looks like it goes on forever because the period is long, and the pattern only stays clean while the numbers are small enough to fit their blocks. The moment they are not, the carries erase the illusion. But saying it is just a rational number does not make it any less lovely. The whole trick is that a single ratio of 2 whole numbers can carry an entire sequence folded up inside it, and long division is the crank that unfolds it back out. The order was never magic. It was engineered digit by the identity underneath. So the mystery empties out into something better than magic, a method. Every one of these fractions is a sequence in disguise. Pick a sequence with a clean rule, write it as the coefficients of an infinite sum, collapse that sum into a compact fraction, and choose a spacing so each term gets its own block of digits. Long division does the rest, reading the sequence straight back off the decimal until the terms grow too big for their slots. Counting gave us 1 over 998,001. Fibonacci gave us its near twin. The same recipe reaches squares, cubes, and far stranger sequences, each hiding inside its own unremarkable-looking fraction. The object mathematicians built to do this on purpose has a name, the generating function, and it is one of the most powerful bookkeeping devices in the subject, precisely because it can pack a whole infinite list into a single closed form. What looked like a party trick, a fraction that counts, is really a small window onto that idea. One number, and folded up inside it, all the others in order. This was another one in the series. Stay for the next.